Hey everybody, your Friendly Math Tutor here with our Unit 3 Advanced Differentiation lecture. So as always, please make sure you subscribe, check out our Instagram and TikTok this week and Facebook for some videos, including a lot of practice problems for this week's topic. Check out our Patreon where we'll have a weekly review, a video with the solutions to that weekly review, and a live Q&A next Friday. All right, so today we are going to focus on more advanced differentiation. And that's going to start with the chain rule. All right, so last week we talked about product rule, quotient rule, power rule. And today we're going to kind of move ahead to the chain rule. So the chain rule is going to be used whenever you have a function inside of another function, so a composite function, and you have to take the derivative of that. So we're going to look at two different notations. One of them is the Leibniz notation, which is going to look something like this. When you have a function defined as y equals and you want to find the derivative of it, we write dy dx, which is the derivative of y with respect to x. And the way it's going to work with Leibniz notation is we're going to do the derivative of y with respect to u multiplied by the derivative of u with respect to x. All right, this is going to be one way that we do it. All right, so to show like how this works here, what I'm going to do is I'm actually going to write this. I'm going to change this. I'm going to make this y. So if we're looking for dy dx, what we need is y in terms of u and then u in terms of x. So what we can think of this as is y equals u cubed, right? This is the sign that's being cubed. So we're writing it as u to the third power. And then we need a u function in terms of x. Well, u is simply just sine x. It's the thing that's being cubed. So look at how this breaks down. This is the sine that's being cubed. So it's the sine, and then sine is u, and then u is being cubed. And then if we want to find dy dx, so the derivative of this original function, we can do dy du, so the derivative of y with respect to u. This is just a power rule. So this is just 3u squared times du dx, so the derivative of this u with respect to x. Well, the derivative of sine x is cosine x. And then finally, we know that u is really equal to sine x. So this is 3 sine squared x times cosine x, all right? That would be our derivative and how the chain rule works. That's actually what's going on in the calculus. Now, you don't need to always do this. I just wanted to go over this just so you understood the notation. There might be some conceptual problems where you would need to know that. But for the most part, what I would do is stick with the Newton notation. So that's what we're going to mostly focus on whenever we do these. And the Newton notation is more of like function notation. So if you have this function f of g of x, so one function inside of another function, and we're trying to do the derivative of that. The way that really works is we're going to do the derivative of the outside function first, and we're going to leave the inside function alone. And then we're going to multiply that by the derivative of the inside function. That's exactly what we did here. We just kind of broke it down more. I would suggest once you kind of understand what's going on, just to kind of do it this way. So what this says is do f prime of g of x. So do the derivative of the outside function first and leave the inside function unchanged. So here, this is different than this. This is another reason I picked these two examples. This is sine cubed of x. Here the outside function was the cube and the inside function was sine. Well, this is the sine of x cubed. So here the outside function is sine and the inside function is x cubed. So if we're going to do the derivative of this, we have to do the derivative of the outside function first. So the derivative of sine is cosine, and the inside function stays the same. Again, derivative, leave the inside function alone. Now multiply by the derivative of the inside function, which is 3x squared. And we could just write this as 3x squared cosine x cubed if you wanted to. All right, so that's how the chain rule works. Either way you look at it, you're doing the derivative of the outside function first, leaving the inside function alone, then multiplied by the derivative of the inside function. That's going to be how we execute the chain rule. Okay, so the next thing that we're going to take a look at, we will get back to the chain rule, is a key type of problem that you're going to see a lot is you're going to have a table of values and you're going to have to be able to just execute the rules. So this is a way to review some of the rules from last week, and then we're going to incorporate the chain rule into this. So the first example that we're going to take a look at is u of x is just some function that's defined as f of x times g of x. And we have to find u prime of 1. So that means we got to find u prime of x first. Well, this is a product. It's a product of f times g. So we have to use the product rule. So the derivative of the first function is f prime of x times the second function, plus the derivative of the second function times the first function. So u prime of 1 would just be plugging in 1 to all of these. So f prime of 1 times g of 1 plus g prime of 1 times f of 1. And then we don't know these functions, but we use the table to help us get all those values. So u prime of 1 is f prime of 1, which they're telling us is 1, times g of 1, which is 2, plus g prime of 1, negative 1, times f of 1, which is 2. So that's 2 plus negative 2, and we get 0. All right, so that's an example of how we can use a table of values to just execute the rules. All right, so now let's take a look at 3 more examples that we could use this table for. All right? All right, so let's take a look at this one. B is defined as h of x is f of x over g of x. So if we want to find the derivative of h, then we have to use the quotient rule because it is a quotient. So if I want to find h prime of x, I'm just going to follow the quotient rule. So derivative of the numerator times the denominator minus derivative of the denominator times the numerator all over the denominator squared. And then I want to plug in 2. So f prime of 2, g of 2 minus g prime of 2, f of 2, all over g squared of whatever 2 is. And then we're just going to look over at the table to get all these values. So f prime of 2 is negative 3. G of 2 is, g of 2 is 0. G prime of 2 is 4. F of 2 is 3. And g of 2 is 0. So what we end up with here is 0 minus 12, so we get negative 12 over 0, which is undefined. Which means it is not differentiable, all right? Which I guess we could have seen from the beginning if we just looked at the fact that g of 2 was undefined. We would have known right away. But I also wanted to go through this just so you could see how you would solve a problem like this, all right? So we do get undefined. All right, for C, R of x is f of g of x. Now we get, so the first 2 examples, we just reviewed the product rule and quotient rule from last week. So here for C, we want to go over the chain rule. So we have a function inside of another function. So if we find the derivative of this, this is our Newton notation for the chain rule. So it's f prime of g of x times g prime of x. So what that looks like for r prime of 2 is f prime of g of 2 times g prime of 2. Well, what we have to do first is find g of 2. Well, g of 2 is 0. And then g prime of 2 is 4. But then we need to know f prime of 0. Well, f prime of 0 is 3. So we get 3 times 4, which is 12. All right? So let's look at one more example where we've got f of g of x cubed. So now we have the chain rule more than one time. So if we look at how we do v prime of x, we do the derivative of the outermost function first, which is f. So f prime, we leave g of x cubed alone. Now we work our way inside. The next most inside function is g. Well, the derivative of g is g prime. But we keep x cubed the same. And finally, we make our way to the very innermost function, which is x cubed, and we have to multiply by the derivative of that. So that's times 3x squared. And now we're just going to plug in 1 to everything. So we have f prime of g of 1 times g prime of 1 times 3 times 1 squared, so that's times 3. And then we've got f prime of g of 1. Well, g of 1 is 2. So we have f prime of 2. Well, g prime of 1 is negative 1. And we still have this 3. So finally, f prime of 2 is negative 3 times negative 1 times 3, which that is positive 9. All right, so that's how we use all of the rules: product rule, quotient rule, chain rule, when we're not given actual functions, but we just have a table of values. You'll see several different problems like this when you're getting ready for the AP test. All right, so the next thing we're going to take a look at, the next major rule, is implicit differentiation. But implicit differentiation, we really want to associate that with the chain rule. It's not a different rule. It's just kind of how we don't solve for y. So up to this point, every derivative we've done, we've explicitly solved for y. It was always y equals, or f of x, which essentially is y. So here, what's going to end up happening is we are going to do implicit differentiation. So we're going to kind of do it indirectly. So we have a function here that we really kind of can't and really don't want to have to solve for y explicitly. So we're just going to take the derivative. But we have to remember that if we were to solve for y explicitly, we would have some function, right? Y would be some function of x. Whether we can actually do it, you could imagine that. Or even if we couldn't, theoretically, we could say, okay, well, there's these x values that definitely depend, there's these y values that definitely depend on what we choose for x. So just pretend that there is some function of x that y can be written as, but we're not going to actually find it. So remembering that, what we're going to do is we're going to do the chain rule here, all right? Several different times. And actually what I'm going to do, let me change this. I'm going to make this x squared y cubed, all right? So what we're going to do is we're going to take the derivative of this. This is a product, so we have to start with the product rule. The derivative of the first is x squared, so the derivative of that is 2x, just like it always was. Keep the second function the same, plus, now, derivative of the second function. Well, the derivative of y cubed is 3y squared, but we have to look at this like the chain rule. Y is some function of x, right? Whether it actually is or theoretically. So we got to think of y as being the outer function. So we do the derivative of the outer function, so that's 3y squared. Then we have to multiply by the derivative of the inner function. Well, we would have to find the derivative of this, but we don't know what it is. So what we do is we just say, well, the derivative of y is dy dx. And then we keep the second function the same, so x squared. So let's take a look at this again. When we do the derivative of sine y, we look at the outer function is sine, so the derivative of that is cosine. But then we have to multiply by the derivative of the inside function. The derivative of y is dy dx, because again, we don't have y solved for in terms of x. If we knew it was like, say, like x cubed, we could just multiply by 3x squared. But we don't know what it is, so we just kind of write dy dx as this kind of placeholder in a way. Equals, but now on the other side, the derivative of x to the fourth is just 4x cubed. We don't have to do the chain rule. But I want you to see the chain rule is always at play. It's what happens in calculus. When you learn these other rules, they encompass all of the rules inside. So we just learned that x to the fourth was 4x cubed. If you want to apply the chain rule, just what's the derivative of x? It's 1. So if we wrote multiply times 1, that would be redundant. We won't need to do that. So the chain rule is always at play. It's just when it's x, since x is the independent variable, the derivative of that is just 1. But the derivative of y, since y depends on x, y is the dependent variable, the derivative of y is dy dx, derivative of y with respect to x. And we use the Leibniz notation for this. You could see y primes in here, but I like the Leibniz notation personally. So then, if we want to solve for dy dx, now it's just some algebra. So I'm going to take these two terms, I'm going to factor the dy dx out, and I get 3y squared plus cosine y. And then I'm going to bring this 2xy cubed over to the other side. So I get 4x cubed minus 2xy cubed. And finally, if I want to get dy dx by itself, I just divide. So I get 4x cubed minus 2xy squared over 3y squared plus cosine y. So that's the derivative. And let's not forget, the derivative is the slope of the tangent line at a specific point on the original curve. Up to this point, we just had x values. It was, let's say, x equals 5. I could plug it in. Now I would need the full coordinate pair because I'd need to replace x with a number and y with a number to give me the full slope at that point. All right, so it still represents the same thing, just a little more complicated. And implicit differentiation, I really want you to make the connection that that is just the chain rule. It's not this new rule you have to learn. It's just building off the chain rule, and then we're still using the rules that we learned before, product rule, derivative of trig functions, power rule. All the rules kind of are just intertwined among themselves. Okay. So the next topic that I want to talk about is inverse functions. So let's look at this graphically. Imagine we have a point here, and we want to find the equation of the tangent line. Or, sorry, the slope of the tangent line. So the slope of this would be just whatever the rise is over the run, just like slope always is. And the rise is the change in y, and the run is the change in x. So we've got our basic formula. Delta y over delta x is the slope. That's the slope of any line, all right? So that's going to describe the slope of, say, a tangent line. Now let's say we have an inverse function. Well, let's recall what an inverse function is. One way to look at an inverse function graphically is it's a reflection over the line y equals x. So if we reflect this curve over the line y equals x, I'm just going to do the best I can. Let's just pretend that that's it. So then this point is going to flip here. And let's say we have a tangent line at that point, and that's going to have its own rise over run, all right? And we're focused on the slope of this line, all right? So the slope of our tangent line. Let's also remember that an inverse function comes from, remember when we were back in, say, Algebra 2 or Algebra 1 and we were solving for inverses, we would switch our x's and y's, right? Because an inverse function undoes the original function, so it takes our outputs and figures out what input gave us that output. So what's happening here is all the inputs and outputs are switching, all right? So if I look at the relationship to the original, so our inverse function, let's say our inverse function, we use this notation, f inverse of x. Our inverse function, all of our x's are our old y's, and all of our y's are our old x's. So our rise over run, if it's its own function, is certainly change in y over change in x. But if we relate it to the original, our change in y is just our old change in x because all of our x's and y's switched. So we really have this. And our change in x is our old change in y because all of our x's and y's switched. So we could just think of our slope as now change in x over change in y. Again, our old x's and y's that described our original function, not on the actual coordinate plane that it's currently on. So it can be a little bit confusing. But the whole point of all of this, I know I got a lot going on here, but the whole takeaway is if all we're doing is switching our x's and y's, then this point that corresponds to the point that was on the original function, the slope at that point should just be the reciprocal of the slope of the original. All right, so that is kind of our key here, is that when you take the derivative of an inverse function, if you don't know the function, if you know what the function is, you just take the derivative using all the rules we learned before. But if you don't know what the function is, you can find the derivative of the original function and just find the slope of the tangent line at that point, and then just take the reciprocal, because again, our x's and y's are all being flipped, so it's going to be kind of related to the old function. It's going to be the run over the rise. So let's see that in action. So what we have is f of x is some function. I made it a function particularly that would be almost impossible, if not actually impossible, to find the inverse of. So what I'm going to do is I'm going to just figure out what point is on this graph. And I'm going to know that because it's going to be g prime of 7. If I want to find g prime of 7 and g is the inverse of x, well, that means 7 is the output to this function. So on the f graph, I have some point something comma 7. And I need to find that point. Well, I can do that simply by just setting this equal to 7. A lot of times these are calculator problems. I made it easy such that it would just be 1, because 1 plus 3 is 4, 4 plus 8 is 12, 12 minus 5 is 7. So this would be kind of hard to solve, I think, algebraically. So most likely this would be like a calculator question. You could just put this into the calculator on the graph and figure out that it was 1. The point of this, though, is this 1, 7 is the point that lives on the f graph. On the g graph, it's the point 7, 1. Everything's been switched. So when we find g prime of 7, what we really want to do is find the slope of this at 1. This point 1, 7 becomes 7, 1, so we're working backwards. We can't find g prime because we don't know what the g function is, but we can find f prime. So we're going to find f prime of x first, which is simply just 3x squared plus 6x plus 8. So I'm just using the power rule for all of those. And now what I want to do is g prime of 7 is going to be related to f prime of 1. 7 is the input for the inverse function, but 1 is the input for the original function that is tied to that point 1, 7 and then 7, 1 on the inverse graph. So I'm going to find f prime of 1. Well, that's 3 plus 6 is 9 plus 8, that's 17. And if I think of this as a fraction like slope, then that means on the tangent line for the original, the slope is up 17 over 1. Well, what's going to happen is at g prime of the same point, I understand 7 and 1 are different, but 1 and 7 are tied together now with this function. 1, 7 becomes 7, 1. So at g prime of 7, the input for the g function, the slope just should be the flipped version or the reciprocal of this slope. So our answer is 1/17. This is not to be confused with the normal line or perpendicular line where you take the opposite reciprocal. For these, you're just taking the reciprocal, right? So that is how we deal with inverse functions, derivatives of inverse functions, okay? All right, let's take a look at our next topic on inverse trig. So first, I'm going to prove the derivative for sine inverse, and then I'm just going to give you the rest, and we're going to use that as an example. So we talked before about just general inverses, but now we're going to find derivatives of very specific inverse trig functions. So let's think about what this is saying. This is some triangle, some right triangle, such that if the sine inverse of x is y, then that means the angle is y, such that the sine of that angle is x. And we think of that as x over 1. So the opposite is x, and the hypotenuse is 1. And if we find the other side, we just do the Pythagorean theorem. So that turns out to be the square root of 1 minus x squared. All right, so let's keep this in mind. This is the triangle that we're dealing with. If I think about this, y equals sine inverse of x is the same as saying that x equals the sine of y. All right, that's saying the same thing. The sine of our angle is equal to x. And then I'm going to take the derivative. Well, now I can do this, what we've learned earlier. We can use implicit differentiation. The derivative of x is simply just 1. And the derivative of sine y, well, this is chain rule. Derivative of sine is cosine, times the derivative of the inside function, the derivative of y, is dy dx. And notice dy dx, that's the derivative of this. So now we could have solved it explicitly, but we didn't know the formula yet. So to get the formula, we have to write it implicitly and then take the derivative. Divide each side by cosine y. I'm actually going to do it this way. So dy dx is 1 divided by cosine y. Well, 1 divided by cosine y is the secant of y. But I don't really want it in terms of y. I want it in terms of the independent variable x. So now I'm going to go back to the triangle. So dy dx, the secant of y, well, the secant is the reciprocal of cosine, as we just saw. So if I want the secant of y is going to be the hypotenuse over the adjacent. So that's 1 over the adjacent side, which is square root of 1 minus x squared. So that is the derivative of sine inverse of x, 1 over root 1 minus x squared. They can all be solved in a similar way. So I'm just going to put that one here. So that's 1 over root 1 minus x squared. That's a derivative of sine inverse. Now, cosine inverse is the same thing, it's just negative. So that's why I have these kind of grouped together. So if you are memorizing these, at least just know that you only have to memorize 3 of them, and all the ones that begin with the letter C are the negatives of the functions that the co-functions that they go with. So cosine goes with sine, cotangent goes with tangent, and cosecant goes with secant. The other ones are tan inverse is 1 over 1 plus x squared. So therefore cotan inverse is negative 1 over 1 plus x squared. And then secant inverse is 1 over the absolute value of x times the square root of x squared minus 1. And cosecant inverse is negative 1 over absolute value of x root x squared minus 1. All right, so these are unfortunately ones that you're just going to kind of have to commit to memory. And then I'm just going to do one example of how you would use these formulas. So let's say we have f of x is sine inverse of x squared plus 2x plus 1. What we're going to do is we're going to use the chain rule. So if I want to find the derivative, so f prime of x, the derivative of sine inverse is 1 over root 1 minus, well, x squared. But they really just mean the input, whatever the input is squared. Well, our input here is our inside function is x squared minus 2, x squared plus 2x plus 1. So I'm just going to put that in parentheses. So that is what this rule is saying. 1 over the square root of 1 minus whatever the input is squared. But we're not finished because that's just the outside function with the inside function in it unchanged. But we have to multiply, we have to use a chain rule. We have to multiply by the derivative of the inside function. And that is simply just 2x plus 2. So you could just start to do it like this. Instead of the 1, just put the derivative up there. So 2x plus 2 over, root 1 minus x squared plus 2x plus 1 squared. All right, we could probably simplify that a little more, but you get the idea. All right, so any one of these rules, any new derivative rule that we learn, we can always apply the chain rule to it if the inside function is not just x. All right? All right, let's take a look at the next topic, higher order derivatives. So this just means, so if we could take the first derivative, then we should be able to take the derivative of the derivative or the derivative of the derivative of the derivative, right? So we just start to name them. First derivative, second derivative, third derivative, and so on. And we have 2 different notations again. So if we look at Newton's notation, we're looking more at like function notation. So it's going to look like this. We've seen this a lot. F prime of x is just the derivative of this. So let's review the chain rule. We're going to do the power rule first because the outer function is this thing being raised to the 4th power. That gives us 12 cosine cubed x. Now we move to the derivative of the inside function, which is negative sine x. I am going to rewrite that as negative 12 sine x cosine cubed x. Now, if we want to take the derivative of the derivative, this is where the higher order comes in. We're going to find what's called the second derivative. We'll do a lot more with this in the next unit or two about what the second derivative means. But right now, you just got to be able to find it. But all you're doing is a derivative of a derivative. So you're just applying the same rules over again. But we got to be careful. We're doing the derivative of this function, which involves a product of two functions of x. So we have to use the product rule. So I could think of this as the first function. I'm going to lump the negative 12 in with it, and then this is the second function. So derivative of the first function is negative 12 cosine x. The second function remains unchanged. Then I got plus the derivative of the second function, which now the derivative of the second function is the chain rule. So that's 3 cosine squared x times the derivative of cosine. Oops, so we get another negative sine x. And then that's multiplied by the first function, negative 12 sine x. All right, so it can get pretty complicated. And then if we want to write this again, this first one could be negative 12 cosine to the fourth x. And then all of this, the two negatives make a positive, so I would get plus 36 cosine squared x sine squared x. That should be correct. And yeah, that looks correct. All right, so that is our second derivative. If we wanted to, we could find the third derivative or the fourth derivative. So basically, we're not going to do that for the sake of time. The third derivative would look like this. And then the fourth derivative, we start to use parentheses and the number. So if you see like f with a little 4 up there, it means find the fourth derivative, 5 would be fifth, and so on. But at least for first, second, and third, we just use the dashes or the primes, whatever you want to call those. So now we look at Leibniz notation. So we got y equals e to the 7x plus 3. The first derivative is going to look like this, dy dx. We have seen that before. Now we're going to do the chain rule. So the derivative of e to a power is e to that power. And then we multiply by the derivative of the inside function, which in this case is 7x plus 3. The derivative of 7x plus 3 is 7. So I'm just going to put a 7 in front. Now, the next derivative looks like this. It looks like it's d squared y dx squared. It's not actually, it kind of is what it is, but this we just have to recognize as the notation. If you replace those with 3s or 4s or 5s, that'd be the third, fourth, fifth derivative, respectively. So all this means is take the derivative of the derivative. So we've got the derivative of e to the 7x plus 3 is e to the 7x plus 3 times the derivative of 7x plus 3, which is 7. But that 7 will multiply by the 7 that's already there, and it will give us 49. So we could just keep going with this and find the third, fourth, fifth derivatives and so on. They are what we call higher order derivatives. So the most important thing, you know how to take a derivative, you just do it again. It's understanding the notation, all right? So if you see this d squared y over dx squared, again, I know that that's not really how you say it, but that's how your brain is probably seeing it when you see it for the first time. This just means second derivative, all right? Second derivative of y with respect to x, okay? All right, and the last thing we're going to do is just a couple review problems, all right? So here we're going to review the chain rule, and we've got our Newton notation, so the derivative is going to be written f prime of x. So here we've got several chains, so I want you to just start again with the outermost function. If you have difficulty thinking about what the outermost function is, imagine order of operations and you plug it into a calculator. What's the first thing you would do? First thing you would do is you would square the number, and again, if you were evaluating a specific value, that's what I meant by that. If you plugged in a number for x, you would square it and add 2 first. First thing you would do, innermost function. Next thing you would do is you would take the tangent. The next thing you would do is the next outer function. And the last thing we would do is we would square it and multiply by 3, but the squaring it is the outermost function, all right? And really, the squaring it and multiplying by 3 are going to go together. So since that's the outermost function, we're going to start with the power rule. So we're going to bring the 2 in front to make 6. Tan to the first power, lower by 1. Everything else stays the same. Tan x squared plus 2. Now we move into the second innermost function, the tangent. So the derivative of tangent is secant squared of x squared plus 2. Now we move into the innermost function, x squared plus 2, and the derivative of that is 2x. So we could best write this as 6 times 2x is 12x tan of x squared plus 2 times secant squared x squared plus 2. And that would be our first derivative. All right. The next one I want to look at is just in Leibniz notation, y equals natural log of x to the 5th plus 3x squared. And that's going to look like this, so dy dx. The derivative of natural log, the way that works is it's 1 over x, but that x is really just because it was the natural log of x. It's really 1 over whatever we're taking the natural log of. But I'm going to skip the 1. I'm just going to put it over x to the 5th plus 3x squared. All right, so imagine a 1 there. That's the derivative of natural log. 1 over whatever we're taking the natural log of. But since we're not taking the natural log of x, it's not just 1 over. We have to do the chain rule. We have to multiply by the derivative of this. And if there was a 1 here and we multiply by the derivative of it, it would just go up in the numerator anyway. So that's why I'm leaving the space. And the derivative of this inside function is 5x to the 4th plus 6x. So essentially, when you're doing natural log, the quickest way to do it is it turns out to just be the derivative of the inside over the original inside. All right, that's the chain rule, but that's just what happens every time. So maybe if you see natural log, you just do this so you can save a step in like simplifying. All right. Okay, the last problem I want to do today, we have not learned how to do yet, but what we're going to do is we're going to apply what we've learned and some pre-calc from before, and we're going to figure this out. So I want you to think about 3 types of derivatives that involve exponents. One of them is just our basic power rule, x squared, x cubed, x to the 4th. We just do power rule, x cubed is 3x squared, all right? That is when we have a variable in the base and our exponent is a real number. Then think about e to the x or a to the x, 7 to the x, 6 to the x, all right? We have a rule for that. That is when we have a new number as our base and our variable is in the exponent. Now let's look at x to the x. That's both. You have a variable in the base and a variable in the exponent. The power rule nor our rules that we talked about last time with exponentials apply to this. So we can't use them. We can't bring the x in front and be like x times x to the x minus 1. That does not work. But what we need to do is, as we always do in math, whenever we have an exponent that has an x in it and we don't want it there, we use logarithms because logarithms are the inverse of exponents. So what we're going to do is we're going to take the natural log of both sides. This is one form of something called logarithmic differentiation. And it'll involve the chain rule eventually, which is why I'm going over it here. So then what we do is we don't want this exponent there. Well, there is an exponent law that allows us to move this in front. We are not doing the power rule. This is kind of like the power rule for logarithms, all right? It's not the power rule for derivatives. So this power can come in front and be a coefficient. So now I don't have an exponent anymore, and I can use the derivative now. But if I took the derivative here, it would have just been dy dx, but I don't have that now. I have the ln of y. So the derivative of natural log is 1 over that times the derivative of the inside function, so dy dx. I understand what I said back here about just doing the derivative over the original, but I didn't want to have a fraction within a fraction, so I did it kind of the old school way here, where it's just 1 over what we're taking the ln of y of, or what we're taking the ln of, times dy dx. All right, dy dx is the derivative of y. That equals, well, on this side, if I take the derivative, I have to use the product rule. The derivative of x is 1 times the natural log of x, plus the derivative of natural log of x, which is 1 over x, times our first function x. So I'll do a couple things here. So I'm going to get dy dx by itself. I'm going to multiply this side by y. And then I have ln x plus these x's cancel to give me 1. And finally, our final answer is going to look like this. Dy dx is y is really x to the x. So I'm going to substitute it back times ln of x plus 1. All right. So if you have a variable in both the base and the exponent, we use this thing called logarithmic differentiation. So in 2 steps, you don't do any calculus. You do 2 steps. You just get it to the point where we don't have a variable in the exponent by taking advantage of our log properties. And then you take implicit differentiation to finish the problem. All right. So I hope that was helpful. That's just kind of a review of everything in Unit 3. So please check out the weekly review, 16 problems on Patreon. Also, stay tuned for the solutions to those later in the week. Check out our TikTok, Instagram, and Facebook, where I'll be just posting AP problems related to this unit this week. All right. Again, hope that helped.